So, hi everyone. Today we're going to study a new exercise, a new problem, which is called Maximal Volume Cone. So, I've got a disc, paper disc here. And what we're going to do is to cut away the radius here, a radius. And we're going to shape a cone by overlapping a part of the paper like this. So we form a cone like this. And the problem is, what we want to know is what's the maximum volume we can give to this cone. We could make a very thin cone like this, very thin. Probably this would have a small volume, and we could make a rather flat, broad cone like this and get maybe a bigger volume. So the question is how to get the maximum volume cone. So let's try and find a solution to this problem. And the first thing we can notice is that when we overlap an angle alpha, we get a base circle of perimeter 2 pi minus alpha. So I can show this. When you cut out or you overlap the angle alpha, then you get a radius for the base circle. You know, the base circle is the disc you've got at the base here, and its radius will be 2 pi minus alpha divided by 2 pi. So we can get the radius of the base disc in terms of alpha. Let's explain this once again. At the beginning we've got a circle of radius 1. Then we overlap an angle alpha. Then the rest of the circumference here would be of length 2 pi minus alpha. And when we overlap these, the base disc will have a length of 2 pi minus alpha. But the radius is the length of the circumference of the circle divided by 2 pi. So we know that r is equal to 2 pi minus alpha divided by 2 pi. This is the radius of the base disc. Now we've got a cone, and this cone has an apothem 1. The apothem is the length here, and it is 1 because the radius of the original disc was 1. So we can calculate the height of our cone, and this height we can figure out by Pythagoras Theorem, because we've got 1 here and the radius r that we have just calculated here. So by Pythagoras Theorem we know that the height of the cone is square root of 1 minus r squared. So if I can show you the cone, then the height of the cone would be the square root of this squared minus the radius squared. So now that we've got the height, we can calculate the volume of the cone. The volume is 1/3 times the area of the basis the area of the base disk is pi times r squared, times the height, and the height is square root of 1 minus r squared. So this is our function, the volume of the cone. And this is the function that we have to maximize. So what's the problem now? We've got a function and we want to maximize it, function of r. And as we do usually, we're going to find the derivative of this function and study the variations of the function. But the problem is, this function is quite complicated. We've got r squared here, we've got a square root, we've got a product, and this is going to be a difficult calculation. As you can see, you can calculate the derivative of the function and figure its sign when it's positive. But this is quite difficult. What I want to show you now is how to simplify this calculation by considering another function. So the point is, when we have this function v, we are a little bothered by the square root, and we can get rid of it just by taking the square of v and everything here. So when we square this, we get v squared is equal to 1 over 9. Let's compare with this original function. V squared is equal to 1 over 9, which is the square of 1/3, times pi squared times r to the power of 4, and the square root disappears and we get 1 minus r squared. So this function is a little bit simpler than the previous one. But we can simplify this once again further, just by noticing that we don't have any r variable in this function v squared. We only have r to the 4th and r squared. So we can set x is equal to r squared and get a new function f, which is v squared. Let's call it f. And this is 1 over 9 pi squared x squared, because r to the 4th is x squared. And 1 minus r squared is 1 minus x. So if you want to maximize the volume, it would be enough to maximize the square of the volume, that is, maximizing the function f in terms of this new variable x, which is r squared. So now we have a much simpler function f, 1 over 9 pi squared x squared times 1 minus x. So now it's pretty easy to calculate the derivative of this function f. 1 over 9 pi squared is a constant, and we differentiate with respect to x. The derivative of x squared is 2x. 1 minus x remains, plus x squared times the derivative of 1 minus x, which is minus 1 or negative 1. Then we calculate this. Minus 2x squared minus x squared, it's minus 3x squared, plus 2x. Why do I have minus 2x here? Okay, so now we've got 1 over 9 pi squared times 1 minus 3x squared plus 2x. We can factorize this by x, and we can see that f prime of x is equal to 0 if and only if minus 3x plus 2 is equal to 0, or x is equal to 0. But if x is equal to 0, then r is equal to 0, and this means that we don't have any cone anymore. So we are not interested in this value of x is equal to 0. Minus 3x plus 2 is equal to 0 when x is equal to 2/3. So the maximum volume of the cone should be reached when x is equal to 2/3. But we know that x is equal to r squared. So if we know that x is equal to 2/3, then we can deduce that r is equal to the square root of 2/3, and the square root of 2/3 is, so r, which is a positive number, should be the square root of 2/3, and from what we said before, we know that r square root of 2/3 is equal to 2 pi minus alpha over 2 pi, and from this we can calculate alpha, which is 2 pi times 1 minus square root of 2/3. This is in radians, and we can convert this into degrees by multiplying by 360 over 2 pi, and then we get alpha is equal to 66 degrees approximately. So our conclusion is that the maximum volume cone would be reached for an overlapping angle alpha of 66 degrees approximately. So we take alpha is equal to 66 degrees, like this, and we get the maximum volume cone.